Okay, so how would we decide? What do we evaluate? Start with charge. So when we look at the stability of the conjugate base, okay, charge. Same. What's the next thing?
Size.
Is there a difference in size? No. Is there a difference in electronegativity? Is there a difference in resonance? Okay. That pause is a little alarming. You need to practice your resonance so that when you look at these things, you can be like, there's no resonance. Your fluidity with identifying whether or not there's resonance should be insanely fast. Okay? The pause that was given there is ballpark unit 2 in OChem 1. I know you guys have been doing a whole hell of a lot more resonance than that. You have the ability to respond a little bit quicker than that. It's okay. I just want to point that out because you're going to get hit with resonance on the exam. What's next? Do you see an inductive effect? Okay, which means? Okay. So, what's in that category? Substitution patterns, hybridization. Okay, so we could go through and see, do we have a hybridization difference?
Yes.
Yeah. This is SP, this one's SP2, this one's SP3. So we do have a hybridization difference. How does that affect the stability of the anion?
Effective electronegativity.
It changes the effective electronegativity. How?
I believe the effective electronegativity increases as the S percentage decreases.
So what you're spitting out is something that it sounds like you've memorized. Okay, we'll come back to that because I haven't memorized it. I have to work my way through it. What did you suggest, Sha?
I said the availability of p orbital.
I would lean against the availability of the p orbital. I think you could make an argument there. What's ultimately the difference?
How many p orbitals as available?
How many p orbitals were used in that hybridization? So what you're comparing is S versus P. Okay? Well, what is the difference between S and P? P is higher in energy. So if P is higher in energy, why is it higher in energy? If I drew an S orbital, where should I draw the P orbital? Is this a good P orbital? Wow, that was fast. That's good. I like that. Why not? Where's the p orbital? What was that? Farther away from the nucleus. It has some part of it that is further away from the nucleus. Why does that matter? If we have more p character, where are those electrons held?
Further away from the nucleus.
Further away from the nucleus. This has less p character, which means the electrons are closer to the nucleus. What does that mean about the ability of the carbon in either of those cases to hold the electrons closer to the nucleus? The SP holds it closer than the SP3. Do we have a way of ranking the difference in atom ability to hold electrons? Electronegativity. This is where we bring in effective electronegativity. The SP atom is effectively more electronegative than the SP3. And because it is effectively more electronegative, what does that mean about the stability of the negative?
It's more stable.
It is more stable. And if the conjugate base is more stable, what does that say about the acidity? It's more acidic. That's where you use induction. Was there a complete and utter cop-out? Always. There's always a cop-out. What's the pKa for the terminal alkyne? I can already tell Abby has chosen not this cop-out. based off of that expression. Oh, same with Charlotte.
Don't know, do not like them.
pKa for the alkyne is about 25. The pKa for the alkene, I think, hovers somewhere around 40. The pKa for the alkane is about 50. What do pKa values mean? It's a rank of acidity. Smaller values are more acidic. Okay? So you could use the raw experimental data, or you could go through and use a hybridization effect to explain that differential. Some pioneering students will say, well, isn't this really just an argument of electronegativity? It is, but the reason why I don't want to put hybridization up in the electronegativity effect is people will start to overemphasize the hybridization effect in electronegativity when the atom identity changes. So if you're comparing oxygen to carbon, oxygen is more electronegative than the carbon. Right? And we could quantify that pretty easily. Quantifying the electronegativity for the sp carbon is not something that's been done or is readily available. Okay? And it is an important one to know because you'll see questions about what base do you use to remove the hydrogen. Okay? And when we look at the alkenes and the alkanes, typically you don't. You don't use any base to remove those hydrogens because they aren't acidic. But with that one, you do use a base to remove those hydrogens. Can you use hydroxide? What's that? Yeah? Okay, and this becomes the fun question, and it is an ACS style question. I don't know if I ask it on your version or not. Okay. This is actually a reaction that I tell you to memorize because it's involving this weird hybridization effect, and it becomes really challenging to nuance. If we compare the conjugate bases, so our negative charges on each side, we're looking at negative oxygen versus negative carbon. Which one's more stable? Negative oxygen, which suggests that reaction does not happen. Okay? So no, I cannot use sodium hydroxide to deprotonate an alkyne. Okay? How else could I do it? I could look at the pKa of the alkyne versus the pKa of water. What's the pKa of water?
14.
15.7. Okay. So I'll give you 16 to make it a little bit easier. Which way does your reaction favor? Less acidic. It again goes back towards the reactants. So hydroxide does not work to do this. Okay? And we can use charge size, electronegativity, all of that to help us out with this. How about sodium hydride?
Yeah.
Why does that one work?
Hydrogen's smaller than carbon.
Hydrogen is insanely small in comparison to that. Carbon, the hydrogen gas is very, very stable, okay, relatively. Okay? And so that one does indeed work, and that follows our standard charge size electronegativity. Okay? The problem with this one and why we typically don't use sodium hydride, well, there's a couple reasons with it. Number one, it's incredibly basic. Okay, and because it is so basic, it can be dangerous to work with. And two, it produces hydrogen gas, and hydrogen gas is a flammable substance, which could mean our whole reaction goes kaboom. Okay, so generally speaking, we try to avoid sodium hydride if there's something weaker that does it. How about sodium amide? And if we go through and evaluate sodium amide, based off the conjugate base, charge, same, size, carbon versus nitrogen, same row, same. Electronegativity,
Nitrogen is more electronegative.
nitrogen's more electronegative, which would suggest
Oh.
what does it suggest? That it is more stable, and we would suggest that we get reactants, which means the only reagent we can use is sodium hydride, or some esoteric random other base. Except when we go through to look at the pKa's, the pKa of ammonia is sitting about 35. What does that mean?
It's gonna be the products.
It favors the products. Why? Because that hybridization effect is just enough to screw you over. Okay? This is why, for this particular reaction, I tell you, you should memorize sodium amide will deprotonate an alkyne.
So in
Right.
this scenario, the effective electronegativity beats out.
Is enough to overcome the actual electronegativity of the atom. Yeah. Doesn't that suck? Okay? And just like we've talked about the entire semester, I tell you, you should memorize the trends so that you have them, and then memorize the exception to the trend. So instead of memorizing 3 things, I'm telling you to memorize 2 things. Whereas one of those things applies to 80% of our reactions. That's why it's important to have that charge size, electronegativity, induction, resonance induction. Oh my God, thing memorized. I like how I said, oh my God, and the 2 of you raised your eyes like, oh, what just happened? Desired effect. Does that help answer your question about hybridization?
Yeah.
Typically, the hybridization question is very specific, and it's very specific to the carbon.